The elements of life. The 6 most important elements of life are summarized by the memory aid S.P.O.N.C.H or S.P.O.N.C.H. S, P, O, N, C, H, S.P.O.N.C.H. The 6 most common elements in living things. S is for sulfur. It's often found in nature as a yellow, foul-smelling mineral with an odor like rotten eggs. It's part of the toxic gases produced by volcanoes. Where do we find sulfur in the periodic table? Atomic number 16. Why do we care about sulfur? Because it plays an important role in protein structure. Specifically, chains of building blocks called amino acids are used to form proteins. And one particular amino acid, called cysteine, has sulfur in it. And the sulfur in one cysteine is attracted to the sulfur in another cysteine. You can see them as the orange circle, like beads on a string. And so these sulfhydryl groups are attracted to one another, and they form what's called a disulfide bridge. Now, for our purposes, what matters is that when you have this long chain, like beads on a necklace, some of the beads are attached to each other, and this affects the way they fold up. It eventually affects the shape of the protein. And as you're going to learn, proteins are all about their shape. Sulfur plays an important role in setting that shape in protein structure. The P in S.P.O.N.C.H is for phosphorus. Phosphorus exists in many forms as a waxy solid. You can see from the illustration here that all the atoms in the picture are the same. They're all phosphorus atoms, but there's different ways that they can be combined to make different shapes. So that's why we have different forms of phosphorus. Where's phosphorus in the periodic table? Why, it's right next to sulfur. Phosphorus, then sulfur, PS. 15 and 16. What is the role of phosphorus in living things? Well, it's very numerous. It plays many roles in the chemistry of the cell. It's required to build nucleic acids like DNA. Here we have what's called a nucleotide of DNA. It's like a single piece of DNA. Every cell in your body has billions and billions of these pieces, but each individual piece of DNA has one phosphorus right there. And we also have energy carrying molecules that like ATP and NADPH, and these often have 1, 2, or even 3 phosphoruses attached. So you need a lot of phosphorus to make these kinds of molecules used by living things. S, P, the O is for oxygen, a highly reactive gas. It makes up 21% of Earth's atmosphere. Where is oxygen in the periodic table? Well, it's right here. 8. Now, oxygen has a nice side, a good side, but it also has a dark side. That dark side is related to the fact that even though oxygen is essential for life, it's also a metabolic poison. It will quickly destroy cellular structures if it's not handled carefully. For example, if oxygen gets into your DNA, it will damage it. And that damage could cause the DNA to fragment. It could lead to changes in the different cell organelles. It can cause all kinds of problems, including cancer. So if oxygen is so dangerous, why do we use it? Well, we use it because it's the most common way of getting a lot of energy. Large organisms made of many cells need a lot of energy. You and I are made of trillions of cells. We need a lot of energy. And so reactions involving oxygen typically provide that energy. These reactions are supposed to happen inside a special chamber called the mitochondria. Oxygen is brought into the cells, but we don't want it just to hang around bumping into stuff and maybe damaging things. We're supposed to put it into a special chamber, the mitochondria. That's where the chemical reactions are supposed to happen. The N in S.P.O.N.C H is for nitrogen, and nitrogen makes up about 78% of Earth's atmosphere, which means most of what we breathe at every given moment is nitrogen. And yet, we can't actually get any nitrogen into our body by breathing in the nitrogen in the air. We breathe it in, but then we breathe it out. It does nothing for us, but it also does nothing to hurt us. Well, why is the nitrogen not available in the atmosphere? Well, it's because it's a diatomic molecule. There's actually two nitrogens, and they're held together not with one, not with two, but with a triple bond. Triple bonds are very strong. It takes a lot of energy to break a triple bond. And we can't do reactions that are that energetic in our bodies. You know, we'd catch on fire. Bad things would happen. So the nitrogen comes in and it goes out. We have to get the nitrogen. We just can't get it from Earth's atmosphere. Now, where is nitrogen in the periodic table? Bam. It's right next to oxygen, number 7. Now, even though we can't get nitrogen from the atmosphere, we're going to have to get it. We definitely need it. It's one of the 6 molecules of life. What do we need it for? Well, remember we needed 1 phosphorus for make 1 building block of DNA. Well, to make 1 building block of DNA, we're going to need 5 nitrogens. 5 nitrogens. This whole structure is called a nucleotide, and you'll later on learn about this structure in greater detail. Notice also we have this thing in the middle that has a big giant red circle labeled nitrogen as part of what's called an amino group. And this is an amino acid. This is a sketch of the building blocks of protein. You've got to have a nitrogen for every amino acid. Every amino acid has this little amino group, and it needs 1 atom of nitrogen. So we need it to build DNA, and we need nitrogen to build proteins. The C in S.P.O.N.C H is carbon. Carbon exists as a solid in many forms, including graphite and diamond. Now, graphite's the big black rock, and it's actually very soft. In fact, there's no difference between the graphite in this rock and the so-called lead in your pencil. The lead in your pencil is actually a soft mineral version of carbon called graphite. Chemically, graphite is almost exactly the same as the hardest naturally occurring substance on Earth, which is diamond. It's the way the carbon atoms that are arranged that makes one soft and makes the other one very hard, and of course, a girl's best friend. Where's carbon in the periodic table? Bam! It's right next to nitrogen and oxygen. It's number 6. The significance of carbon is that it is used to make chains and straight chains and folded chains and rings and all kinds of shapes. Carbon has an ability to hook a lot of different things to it and to form a lot of different shapes. And that's because it has the ability to form multiple bonds in many directions. So we have what are called monomers and polymers. Monomers are the building blocks, the general terms for the building blocks. And polymers are the chains that are made from these building blocks. And in the particular case of proteins, these chains can become very complicated and have really complex shapes, which is good because we often need to make really very specific shaped molecules to do specific things. The chemistry of life is definitely based on carbon. At the tail end of S.P.O.N.C H, we've got hydrogen. Hydrogen, of course, is element number 1. It's an explosive gas. Because it's so small, it often loses its lone electron, and that means it exists as a single particle, a proton, which has a positive charge. And sometimes we'll say hydrogen ion, and sometimes we'll say H+, and sometimes we'll say proton, but all those words and phrases just mean the same thing. They mean the nucleus of a hydrogen atom with no electron. And it has an overall charge of +1. Hydrogen is the simplest element, so you won't be surprise to know that its atomic number is 1. Less obviously, since hydrogen is the simplest element, it's very useful as a basic building block of a lot of other molecules that are pretty simple, things like water, or other molecules that have simple repeating shapes. We're going to learn that one particular kind of simple repeating shape is a hydrocarbon, which is just a molecule made from hydrogen and carbon. And we also have very similar carbohydrates. And that's a molecule that's made from a chain of carbon atoms surrounded by the building blocks of water. Hydrocarbons are things like, candle wax and gasoline, whereas carbs, that includes the sugars, the quick, easily dissolved molecules that so many of us like in our foods. Now, in addition to S.P.O.N.C H, sulfur, phosphorus, oxygen, nitrogen, carbon, and hydrogen, the 6 main elements in living things, we also have what are called trace elements, and I want to mention a couple. So in humans, calcium plays a role in making bones and teeth, while iron is required to make a key component of blood. You only need one iron atom to do it, but you've got to have at least one iron atom to make a working red blood cell. Everything else works, but the iron atom is not there, it won't do its job. So these are definitely trace amounts, but they're critical for particular kinds of cells. We also see sodium, magnesium, chlorine, potassium, and other things that have an overall positive or negative charge. Just like calcium, these are called ions. And these are needed in small amounts, typically, but the smaller amounts are doing a lot of work, even though they're very small, because by having a charge, moving these molecules around moves electrical charges around. And so we use things like sodium ion or magnesium ion or potassium ion. We use it for carrying electric charges through neurons and other kinds of cells. So calcium in bone, sodium potassium ions in a neuron, iron ions in a blood cell, calcium ions in bones and teeth. So that's S.P.O.N.C H, S.P.O.N.C.H. And now I want to summarize this information about these important and useful elements in a way that will make it real. We have a simplified version of the periodic table. We're not showing all the elements, we're just doing a few select boxes. But these are all mostly elements that are 20 or less in the periodic table. And one group of elements on one side is the metals, and anything on the other side of the stair-step line, of course, is a non-metal. Your instructions are as follows. To complete this table, you need to write in the symbol and the name of the elements that belong in those boxes. Once you've done that, you need to take a green colored pencil, and I want you to shade the 6 most important elements of living things. I want you to shade S.P.O.N.C H where they appear. These are all non-metals, and so they should be easy to find. And any of the common metals that are also used by living things, say like calcium, I want you to shade them blue. So this will be the last task that you'll be asked to accomplish on Friday's lesson. And well, just to be clear, at the end of Friday's lesson, I expect you to hand in things. If you haven't yet handed in your composition book with the completed lab, the drawings on the microscope lab, you need to do that. If you haven't yet completed page 4 and parts of page 5 in your study guide, you should have been doing that while watching this video. And whether you've completed or not, if you are in class today and you have your study guide, you need to make sure it is returned to the instructor that day and clipped aside for whatever period you're in. So first period's all going to get clipped together with a yellow paper clip, and period 3 orange, and period 4 red, and period 6 blue, and then period 7 green, right? You'll be clipped together. We're going to take that work and we're going to store it, because none of us are finished with our study guides yet. None of them are finished, and we don't want them just to sit for 10 days in a backpack. You know, there's a likely chance that some of them will get torn, ripped, or they'll get lost, right? So we just need to hold on to that work because it's not complete. And that way you'll know if you leave it here, we'll have it, and you can go and enjoy your holiday.